Okay, so we're still working on exercise 5.1.3. This is now part 3 of the exercise. And where I left off in the second video was we're working on the basically n equal 2 term of the propagator. And so I'm going to start off not with this reduced form, but with the original one with all of the 2 factorial and 2 to the 2 power. So basically, we have to apply the propagator to our wave function. And what we have is alpha squared over 2 factorial 2 to the power 2, the 4th order derivative of the Taylor series, n equals 0 minus 1 to the n power x to the 2n divided by 2 to the n factorial. Okay, so if we follow the same kind of logic that we used with the first order term, we basically just have to take this derivative of x to the 2n power 4 times. So that would give us 2 to the n times 2n minus 1 times 2n minus 2 times 2n minus 3 times x to the 2n minus 4 power. Okay, so if we put that back inside the Taylor expansion, then we have alpha squared 2 factorial 2 to the 2 power times, now this is n to the 2, because again, if we're taking so many derivatives, then only things with the a higher power in x, x to the higher power, is going to survive. So n equals 0, n equal 1, eventually, since there isn't to a power of 4, then those things are eventually going to take the derivative of a constant, and it's going to be equal to 0. So we have n to the 2 to infinity of minus 1 to the n power times 2 to the n, 2n minus 1, 2n minus 2, 2n minus 3, x to the 2n minus 4 power divided by 2 to the n factorial. Okay, so now we can rewrite this like we did previously. Where we replace those 4 terms in the numerator right up here with a factorial. So that would be 2 to the n factorial now divided by 2 to the n minus 4 factorial, all the terms that were missing in the numerator. And now this one we can rewrite as a double factorial, 2 to the n minus 1 double factorial. That gets rid of the n factorial and 2 to the n in the denominator. And we're left with 2n minus 4 factorial in the denominator. Okay, so a pattern now is kind of emerging where you're going to end up with this double factorial in the numerator and then a 2 to the n minus something factorial in the denominator. And if you notice, we have the same term here, 2 to the n minus 4 factorial and 2 to the n minus 4 as the power. So that matches with what we have. And we also have this 2 to the n minus 1 double factorial term. And so what we could do is we could try and generalize this. So to some index, we'll call it not m, but something like s. Where now what we have is 1 over s factorial times alpha to the s power divided by 2 to the s power. And now we're going to take the 2s derivative of the wave function. Like so. And if it fit with the pattern that we have above, then what this should be equal to is alpha to the s power over 2 to the s power s factorial times the sum n starting from s to infinity minus 1 to the n power 2n minus 1 double factorial x to the 2n minus 2s divided by 2n minus 2s factorial. So we now have one for every single term in our expansion of the propagator. So now what we can do is we could basically write this out, and what we get, we could write it out for all terms of the propagator, and what we would get is oh, I'm sorry. So what we could look at is basically this all the terms where n is equal to s, and what we would have is basically a sum. So for the first term out front, we would have 1. So that's the n equals 0 term. And then for n equal 1, we had alpha over 2. And then for n equal 2, we had alpha squared divided by 2 factorial times 3 halves times 1 half. For the next term, for the n equals 3 term, or I say the s equals 3 term, alpha cubed over 3 factorial and times basically 5 times 3 times 1, so that's the double factorial, divided by 2 times 2 times 2, so that's the 2 to the power of s, plus dot dot dot. And so what we have now, if we're basically what we're doing is what the problem said in the book, let's group together terms in x to a certain power, and these would be the coefficients in front of those terms. And so we can actually write this now of those terms as the sum of minus 1 to the s power alpha to the s 2s minus 1 double factorial divided by 2 to the s power s factorial. So remember, what we're doing is, we're taking, we have to add up all of those sums that we got from each of the terms in the expansion of the propagator. And so when we group together those terms, because there's, the first term when n equals 0, and then there was a summation when n equals 1, there was a summation when we started with n equals 2, the second term, so forth and so on. So anyway, what we're left with then, when we collect all of the, if we collect all of the x to the 2n terms, oh, I'm sorry. If we collect all the 2 to the r terms, where r is now equal to n minus s, because remember, n minus s, all of our terms in the expansion, if you look back up here in the general case, was 2n minus 2s. So we've defined something called r. Then what we can do is we can substitution back into the equation for the terms. So the sum, s equals 0 to infinity, of alpha to the s power divided by 2 to the s factorial minus 1 s plus r. So we replaced n. And then we replaced n in the double factorial, 2s plus 2r minus 1 double factorial divided by 2 to the r factorial. What we get, basically, in is 1 plus alpha to the power minus r minus 1/2. Okay, so finally, what we are left with is this wave function, psi, which is, if I put back in the pi to the 1/4 power, and I now add in the summation of terms, now with my index r, I have minus 1 to the r power over 2 to the r factorial, 1 plus alpha minus r minus 1/2 times x to the 2r power. So I collected all those 2r powers. I now have reduced all of those other terms, and what we're left with is something that looks like this. Where we can now write this as 1 over pi to the 1/4. Well, actually I'll stop here. In the next video, what we'll do is we'll actually try and reduce it a little further and try and get away from a Taylor expansion and get to a exponential.